Okay, we're going to continue this introductory chapter on general chemistry. This is Dr. E again. In this second video lesson, we're going to talk about measurements. First video lesson, we talked about the methods of science, the scientific method, about making observations, coming up with hypotheses, experimentally testing these hypotheses, etc., to lead to laws and theories. Well, for scientists to do their business, they have to be able to measure things and be able to measure them reproducibly. And scientists from different locations have to be able to come up with similar measurements. And this was not only true of science, but also true of commerce and building ships, building buildings, and agriculture, for example. So through the history of mankind, there were a number of systems of measurements that came about, many of them local measurements. You've heard of like the cubit, you've heard of like feet and pound and the hand and the girth and the furlong and various types of measurements of length and mass and time. So various countries had various different systems of measurement. Well, in 1668, a group of countries got together and they decided to come up with a common system of units of measure. That's what we call now the international systems of measurement. And the basic types of measurements are shown on the left: length and mass and time and temperature, amount of substance, electric current, luminosity. We won't deal with the latter two very much. And one of the derived measurements would be volume, which is really an extension of length. We measure length now in meters and centimeters. We measure mass in kilograms or grams, volume in liters or milliliters, time in seconds, temperature in Kelvin or degrees centigrade, the amount of substance in a mole. Now, I think it's kind of important for you to hold on. I'm watching Usain Bolt run the 200 meters in the Olympics. That didn't take very long. I think it's always good that we have some mind's eye view of what some of these measurements are. A meter, you're probably familiar with. It's a little bit longer than a yard. We all sort of know what a yard, you've seen a yardstick. A meter is a little bit longer. A centimeter is actually sort of the distance of your across of your small fingernail of your pinky. A gram for mass, an M&M, a common non-peanut. A regular M&M weighs almost a gram. Sometimes people say a medium-sized paper clip weighs a gram. For volume, a liter is about a quart, and you've probably heard about a liter of beer. But if you have two regular size now bottles of Coca-Cola or any other soda, these are 500 milliliters each. So that'll give you some idea. Also, each one weighs just a little bit more than a pound. So if you sort of need to know how much is a pound, it's a Coca-Cola. And a liter is 2 Coca-Colas. And of course, you have bought sodas in 1 liter and 2 liter sizes. Time is measured in seconds, and it's conveniently how long it takes to say 1 Mississippi, 2 Mississippi. Or in the old days, 1 Tigris-Euphrates, 2 Tigris-Euphrates. Temperature is measured with different scales, and we'll get to that in a second, and the amount of substance is measured in moles, and we'll be talking about that as we go. Some common interconversions, since we in the United States use the English system more than the international system of measurements, or what we call the metric system. An inch is equal to 2.54 centimeters. That's one that you need to sort of have in your back pocket and be able to use when necessary. Another one is a pound is approximately equal to 454 grams. So one of these bottles of Coca-Cola, which I said weighs about a pound, also weighs about 450 grams. And 1 liter is approximately equal to 1 quart. Now, let's talk a little bit about temperature scales. Now, if you look at the bottom right of this slide, I show that the two temperature scales that we're most familiar with are Fahrenheit, which we referred to in the United States most often, and Celsius, which is used in just about all of the countries. So if you're traveling to Canada or to France, you'll have to adjust to the temperature measurements in Celsius. Both of these temperature scales are based on the freezing point and boiling point of water. In the Fahrenheit scale, water freezes at 32 degrees Fahrenheit and boils at 212. And there's 180 degrees or 180 steps in between the freezing point and the boiling point. So remember, 180 steps. For the Celsius or centigrade scale, there are 100 degrees or 100 steps between the freezing of water at 0 and the boiling at 100. So in other words, the steps of the centigrade or Celsius are a little bit larger steps than the ones in Fahrenheit because there are more of these little steps, Fahrenheit steps. Also notice that there's an offset of 32 degrees because in the Celsius scale, water freezes at 0, but in the Fahrenheit scale, it freezes at 32. So we have this offset. Now, if you understand those relationships between the two scales, then it's quite easy for you to appreciate the equation that we often use to convert between centigrade and Fahrenheit, which is 9/5 times the value in centigrade plus 32 degrees equals degrees in Fahrenheit. So where does the 9/5 comes from? Well, clearly it's the ratio of 180 divided by 100. It's the different step size between the two scales. And the 32 is the offset. So this equation is one that you will find comes in handy in converting between Fahrenheit and centigrade. And you can also write another equation to go the other way around and go from Fahrenheit to centigrade. And my advice is always just to know one equation and do a little bit of algebra when necessary to convert from one to the other. Some other issues related to scientific measurements. One is the concepts of precision and accuracy. These two terms are not the same, although they're oftentimes used together or used in similar contexts. Precision is how well repeated measurements agree with one another, and accuracy is how well a measurement is to the true value, if in fact the true value can be known. And a good way of explaining the difference between precision and accuracy is to consider the bullseye sort of analogy, which is shown in the bottom right, where I show 4 different bullseyes. And you can imagine someone shooting a bow and arrow at the center of a bullseye. If you look at the pattern in number 4, the archer, in this case, is both accurate and precise. That is, if you average all of his attempts, all of the measurement attempts, or all the bullseye, or all the arrows that he's shooting at the bullseye, they average around the center, around what is probably the true value, and the pattern is very tight pattern. The tight pattern means that every attempt gives about the same value, and the fact that it's at the bullseye means that it returns something close to the true value, accurate and precise. If you look at number 3, here we have a very tight pattern. So in this case, the archer is very precise with his shooting at the bullseye, but is missing the true value, is missing the bullseye. So case number 3 would be a precise measurement, but not an accurate measurement. The top 2 bullseyes are examples in which the archer is not very precise at all. But in number 2, even though the archer is not precise, if you averaged over a number of attempts, the average would be right at the bullseye, whereas in number 1 just has problems because he's neither accurate nor precise. Now, you will learn later on that random errors, which can oftentimes be due to electrical noise, can lead to losses in both precision and accuracy. A second type of error, what we call systematic errors, which are oftentimes due to a miscalibrated instrument. And those are more like the example 3 in the bullseye pattern, where if you made a correction, you could actually adjust the measurement to the true value. So random errors and systematic errors. Other terms that you need to know about are the use of scientific notations. And of course, now our calculators always give us values in scientific notation, so that's not a topic that you need to worry too much about. But significant figures is one that's kind of a little bit problematic because we're oftentimes misled by our calculator and we're tempted to report more significant figures than we actually should. My advice here is to take a few minutes and look through the pages in the textbook. This is kind of a boring thing to go over in class. I'll admit that. But basically, the issue is that when numbers are measured experimentally, and that when we add or multiply these together, the resultant product or sum can have no more significant figures than the least accurate measurement. That's basically the concept. And to give you an example, in a math class, if you're asked to add 5 plus 0.0092, you would return a value of 5.0092. And I guess that would be right in a math class. But in a science class where you're measuring numbers, if you have 5, such as a 5-pound bag of sugar, if you have 5, and you add to that 0.0092, which is approximately the mass of a teaspoon of sugar, if someone asked you what is the sum of 5 pounds of sugar plus a teaspoon, you would have to say it's a 5-pound bag of sugar. That's because you would know that that teaspoon is a very, very small component and that the 5 pounds is plus or minus probably more than 1 teaspoon. So scientific measurements, be careful not to carry too many significant figures. Or as I say here, a 5-pound sugar plus a teaspoon is just a 5-pound bag of sugar. Now also you'll have to become very good at converting between dimensions. Often in a problem you'll be given a length in meters and you'll need to convert it to centimeters. Well, that's easy, but maybe you're given the length in inches or yards and you have to convert, or miles, and you have to convert it to centimeters. You may be given the mass in pounds and have to convert it to grams. So this is what I mean by dimensional interconversions. Basically, the way we do this, it's a common process, and we handle them always the same, is we multiply the number that we're starting with by a conversion factor that is really an identity factor. I'll explain more what I mean by that, to get the product in the new unit. Now, what do I mean by an identity factor? Well, we just said that 453 grams is equal to 1 pound. So if you look at the table below, if you have an initial measured value in pounds and you want to convert it to grams, you multiply by a factor, a conversion factor, that is essentially a unity factor. That is 453 grams is equal to 1 pound, or A equals B. 453 grams is equal to 1 pound. So anytime I have A equals B, I can say A divided by B is equal to 1. That's what I mean by an identity factor. So you just have to multiply by the conversion factor with the unit that you want being in the numerator and the unit that you want to rid in the denominator so that they cancel. Okay, so if you had 10 pounds, you would multiply by 453 over 1. The pounds would cancel out and you'd get the answer in grams. Likewise, if you wanted to convert between pounds and kilograms, I'll show you the conversion factor, inches to centimeters, or centimeters to inches, 2.54 centimeters in an inch, 1.609 kilometers in a mile, 1.057 quarts in a liter. And similarly, if you want to convert from an SI metric unit to an English unit, that is, if you want to convert grams to pounds, you would do the same kind of operation, except now the English unit would be in the numerator and the unit you wanted to rid yourself of, the metric unit, would be in the denominator. So if you wanted to convert so many grams, like 10 grams to pounds, you would multiply 10 grams by the ratio, this identity ratio of 1 pound divided by 453 grams. And that would give you an answer in pounds. And likewise for all of the other conversion factors. And there are other conversion factors that you can find in the back of the textbook. Now we also use prefixes a great deal in science because we have numbers that are much larger than our base unit or much smaller than our base unit. And this kind of table you can find in a textbook, and you can Google it and find it in a lot of places. But for example, if we say deca some unit, like decameter, that means multiply by 10, hecta, 100, kilo, which we use a lot. Kilo means 1,000 times. So a kilometer, a kilometer, or a kilogram would be 1,000 grams. Kilometer, 1,000 meters. Mega is a million, 10 to the 6th. Giga, 10 to the 9th. And likewise, if we get smaller, we're pretty familiar with centi, like centimeter. That would be 0.01 or 1/100th of a meter. Millimeter or milligram, 1,000th. Micro, 1 divided by 10 to the 6th, 1/1,000,000th. Nano, 10 to the minus 9th. Pico, 10 to the minus 12th, etc. So we will be using these prefixes a great deal. It will just make more sense to talk about units in certain dimensions, like in centimeters and milligrams, etc. Now let's work an example of this conversion of one dimension to another, because sometimes people get hung up about this and they think it's more difficult than it is. It's really not very difficult. So let's say that we have 11 inches. Now your sheet of paper is 8.5 by 11, right? Centimeters. So if someone were to ask you what is the long dimension of a sheet of paper, not in inches, 11 inches, not in inches, but in centimeters, what do? Well, you multiply that 11 inches by one of these conversion factors. 2.54 centimeters equals 1 inch. I think I can remember that one. 2.54 centimeters equal to an inch. So I set up this conversion factor so that the inches is in the denominator, so it'll cancel out, and the unit I want to end up with, centimeters, is in the numerator, so that the inches will cancel out, giving me the product of 27.9 centimeters. See, that's all it is. Now, you might want to try one for yourself, given that there are 8 furlongs in a mile. You knew that, right? 8 furlongs in a mile. And a furlong is 201.168 meters. Probably didn't know that. So 8 furlongs in a mile, and 1 furlong is 201.168 meters. Convert 14 furlongs, that would be a pretty long horse race, 14 furlongs to miles. And then convert this number of miles to meters. So just an example for you to work on. Now, one thing to point out is that when we have definitions, like 8 furlongs is equal to a mile, we assume that those are exact, unless we're told otherwise, and so that does not become the limiting number in terms of significant figures, okay? Because that's a known or established relationship, 8 furlongs in a mile. Okay, now I'd like to close this introductory chapter by just having you work a math quiz, a self-check quiz. And note what I say here, and take this to heart. Answer these without using any electronic device. No calculator, no computer, no cell phone. Okay, I doubt anyone has a slide rule. But you should be able to come up with the approximate answer for these, or in some cases, exact answers. For example, the first one, I got 126 in the parentheses and raised to the 1/3. What's the approximate, not necessarily exact, but the approximate value? ln. ln and then parentheses 2000. What is that ln? It's on my calculator. I remember seeing it. What does it mean? What's ln of 2000, approximately? Another one, I've got these, what are called pipes, these vertical lines, and then inside of it I got -3 raised to the power 3. What's that value? And I've got 0.01 plus 6.32 times 10 to the -7th. These are measured values. What would the answer be? And for ax squared plus bx plus c equals 0, what is the general solution for x? That's something you need to know the rest of your life, what the solution for that equation is. And then what is the approximate volume of a sphere having a radius of 2 meters? And I say below, if you can't do these without an electronic device, there is a math review in the back of the textbook. And I say, and/or call your high school math teacher and ask why he or she allows you to use a calculator in your math class. Okay, that's the introductory chapter. We'll begin the next chapter, which will deal with atoms, some real chemistry. See you in a while.